Okay. Yeah, hi, I'm Ludwig, a PhD student from Stockholm, and I want to talk about neutrinos from the galactic plane for a while. So my idea is that this talk is a kind of two-parter. So first, I'm going to make a small refresher on IceCube galactic plane results already published. And then in the end, I will give a little teaser for next week's ICRC in the hope that I can hype you up a bit. Okay, so here I decided to put some physics on the slide. So why do we expect neutrinos from the galactic plane? The idea is very simple. We have cosmic rays. They traverse or diffuse throughout the galaxy. At some point, they will interact with the interstellar medium. And in the hadronic pp interactions there, you produce pions, charged pions and neutral pions. And the charged pions decay eventually to 3 neutrinos. And then we can make use of the fact that by a rough back on the envelope estimate, we produce for every pi plus, 1 pi minus, and 1 pi 0. And with that, we can, as I show here, somehow relate the gamma ray fluxes to the neutrino fluxes. So as in many forms of astronomy, the galactic plane is the most prominent source in the sky. It's the biggest. And here we have the gamma ray observations, and now we can basically convert this gamma ray expectation to a neutrino flux expectation. Okay, and then there's one more thing to keep in mind to follow what I'm talking about is that, as you heard before, IceCube has 2 different main event topologies. We have mu tracks, which our best tracks we can reconstruct up to 0.1 degree. On average, it's more like 1 degree. And then we have cascades, which are more spherical in the light deposition, so it's harder to reconstruct. And there we more or less have an average angular resolution of 4 to 8 degrees. Okay, and IceCube is at the South Pole, and to get rid of the atmospheric muon background, as you know, we basically use the Earth, which means that classically, the galactic plane is a very, very hard target for IceCube to find. The center of the galactic plane is in the southern sky. We're mostly sensitive to the northern sky. As you also see here in this plot, the galactic center is right about at 0.5 sign deck. And you basically see how our sensitivity grows worse. So in 2017, we published the first analysis trying to find the galactic plane using template fits, which I will talk about a bit more later. And they used tracks. And yeah, basically they were only able to arrive at upper limits with a 1.5 sigma result in the end. But as you know, 2 years ago, we announced the observation of the galactic plane, and this is the point where I highlight the people who actually did the analysis, which was not me. But the result is that we tested 3 different models, and these 3 models exactly come from converting the gamma ray measurements to a neutrino flux prediction. The details are a bit more complicated than just taking the measurements and converting them. You also simulate cosmic ray propagation through the galaxy and so on. But yeah, in the end, the trials corrected p-value was 4.5 sigma, which makes it, I believe, the strongest neutrino source in the sky currently. And the galactic plane flux contributes approximately 10% to the complete astrophysical flux. And here you also see the resulting flux distributions based on these models. So now the question obviously is, how did we in 5 years jump from 1.5 sigma to 4.5 sigma? And the trick in that is cascade events. So cascade events basically open up analyses for the southern sky. So here we have a downgoing cascade, which is obviously not a muon. So we know we have a neutrino there. So these cascades basically give us a way better sensitivity in the southern sky. And the question is, why didn't we do it earlier with cascades? Well, we basically developed a machine learning-based event selection for cascades, which increased the effective area by a factor of 20. So the cascade datasets we're using for this analysis has 60,000 cascades. The previous dataset had, I think, 2,000 cascades. So this is really where the jump in sensitivity is coming from. At one point, we had to analyze 2,000 cascades, and now we have 60,000 cascades. This is where the power of the analysis is coming from. And now I'm going to go a bit through how this analysis actually works and what this analysis really does. So we start with one of those predictions for diffuse neutrino emission from the galactic plane. So this is the flux at 100 TeV for nu anti-nu in logarithmic colors. Yeah, so basically, if you look at this flux predictions, the galactic plane is more or less just a line. All these nice features you see there are basically coming from the logarithmic color scale. Then you convert the expected neutrino flux to your detector expectation. So your IceCube is still in the cascades, a tiny bit less sensitive in the southern sky. So you have to correct for that you will, because of your sensitivity, you will see a bit less but in the southern sky. Since I use the cascade data set, you don't really see that in these two pictures, but this is an acceptance corrected map. And then comes the most crucial part, is that you basically have to smear the templates for your angular uncertainty. So every event in this data set has one estimated angular uncertainty, and we then evaluate this template, not in the raw form, but with, as you can see here, a smeared form. So this is for 3 degrees smearing. And then we can go further, 4 degrees, 5 degrees, 6 degrees, 7 degrees. And this is eventually, 7 degrees is what we quote as the median angular uncertainty for the data set. So this is about what IceCube can see from the galactic plane. So all these super fine details in the end get washed out by our angular uncertainties with cascades. And then you basically use that as your prediction for the spatial PDF. Another thing I should mention is that the analysis used a fixed flux prediction. So it used 3 different models, and one of the models just was a fixed 2.7 Fowler law, and the KRG models have a bit finer energy distribution. And now the question is like, okay, we've seen the galactic plane with 4.5 sigma. What can we do with it? And one thing we did in the paper published in Science, for example, is take our best fit result and compare to gamma ray measurements by Tibet AS gamma. So they measure approximately in the same energy region as our data set is. So we can convert their flux to a neutrino flux equivalent and basically compare, are we consistent with them? They had 2 analysis regions. I cutted them out here as A and B. And basically in these analysis regions, so here this should be A and this is B, they had these 3 data points and these 3 data points. And then we scaled our best flux prediction to this region. And as you see, especially with the pi0 model, it kind of seems consistent. The big caveat here is that this is not an independent reanalysis of the data or anything. This is just taking the all-sky flux and restraining it to that thing. So really the lines here are mostly driven from everything outside that region. So we can do some comparison, but it's not really a true prediction for the, not very true for the data. Okay, and this brings me to my teaser for ICRC. So what I've been working on in this is an analysis which releases the dependence on the model predictions. So the idea is quite simple. Instead of taking these very intricate models, you take just boxes in the sky, for example, the inner and the outer galaxy, and then you do a simultaneous fit, fitting the neutrino flux in each of those boxes. and also the spectral index. So what this analysis then can do is really in each of those regions of the sky fit a spectral index, which was not done before. So we will arrive at the neutrino spectral index in the inner galaxy, and also independent flux normalization. Then you have to decide how to split up your galactic plane. We decided on those 8 different segmentation schemes. So we have some more generic segmentation schemes, which just divides it, for example, into the inner and outer galaxy. And then we have segmentation schemes which are designed exactly so that we're able to compare our data to gamma ray measurements. Okay, this brings me to my last slide. So conclusion, IceCube is not done with the galaxy yet. There's more to come. I work on a more model-independent measurement, and then also I want to tease another PhD student's work a bit from Matthias Thiesmeier, who's a PhD student in medicine. And he repeats the galactic plane template analyses with the carrier gamma templates and so on, but using an updated data set with combined flavors, so cascades and through-going tracks and starting tracks, and also a few more years of data. Thanks for listening.
Thank you, Ludwig. Are there any questions?
Yeah, so just to thanks for your talk. It was quite nice. Just to understand something, when the data sets went from 2,000 to 60,000, was that due to machine learning being able to use older data sets, or was it just due to us being more recent and having more data points in general?
No, so the earlier data set was 7 years, and the DNN cascade data set, which we're using right now, is 10 years. So there was a 50% increase in time. But really the power comes from this machine learning based selection.
And is this then only restricted to IceCube, or could you also apply it to other detectors? Is this to Kamiokande or something?
Okay, about Kamiokande, I have no idea. But if we talk about KM3net, they for sure could do something else. Okay. Because basically, if you don't do a machine learning based event selection, you kind of have to rely on some more hard cuts. And the way that was done before for finding cascades is basically using veto layers. So looking if the outer layers of the DOMs kind of have hits in them. And if they don't, the kind of interaction must have happened inside the detector, but this basically reduces your volume drastically. Yeah. And this machine learning based approach is able to find so many more events, even corner clippers, which are right on the corner of the detector, but obviously a cascade and so on. So that's really where the power comes from.
Right, thank you.
Are there any other questions? If not, let's thank Ludwig again. And I would like to thank all the speakers for being on.